The subject of this tutorial is an integrated look at the dynamics of linear circuits. Circuits comprised of R's, L's, C's, linearly dependent generators and the like. Now, we've spent quite a lot of time on separate aspects of the question of how to describe the dynamic, that is, the time-dependent behavior of such circuits. We first looked at transient response, starting with first-order circuits, one with just one energy storage element, and learned how to describe the behavior of such a circuit when excited by a step or an impulse or some other source, how to describe the behavior as a function of time. We did that also for second-order circuits in an underdamped mode in which we had oscillatory behavior. And then we turned to a different subject, that of sinusoidal steady-state analysis, in which we represented the time function not as a sine or a cosine, but as e to the j omega t, some complex number times e to the j omega t, recognizing that to get back to the real world of time functions, sinusoidal time functions, we take the real part of the excitation or the response anywhere in the network, and that brings us back to real time functions. Now, the point I want to make today is the analysis that you do in a circuit in which you represent inductors by their impedance, Ls, where S is a complex number, and capacitance, the impedance of a capacitance by 1 over Cs, where S is that same complex variable. You end up with impedance, expressions for impedance of a network, or expressions for the reciprocal of an impedance and admittance, or you end up sometimes with transfer functions, voltage transfer functions, ratio of a voltage one place to one somewhere else, or a current one place to a voltage somewhere else. But you end up with functions of S in which R, L, and C appear as parameters, functions of S which can generally be represented as ratios of polynomials in S. And I would like to talk now about the utility of those functions of S, apart from what you already know about, which is that they form the basis for writing the frequency response, for describing the frequency response of a circuit. And keep in mind that all these comments, while expressed in circuit terms, apply equally well to any system which can be modeled in linear terms, that is, which can be modeled in terms of constant coefficients and linear differential equations. To make this a little more concrete, let's look at a specific circuit example. So here's a circuit with two resistors, R1, R2, two capacitors, C1, C2. It's excited, driven by a voltage. Talking here, sinusoidal steady-state excitations, driven by a voltage which I'll represent by V sub I bar. That's the complex amplitude of the input voltage. And we're interested in the complex amplitude of the voltage at these terminals, which I'll call V sub O, the output voltage, complex amplitude. This is a circuit which you've seen before in homework. It has the capacity of functioning as a bandpass filter. If we choose these elements properly, in particular, if this capacitor C1 is bigger than C2, more precisely if the time constant R1C1 is much, much larger than the time constant R2C2, there's a range of frequencies in which neither capacitor, in which this capacitor looks like an open circuit and in which this capacitor looks like a short circuit. And in that case, this is simply a voltage divider, and the voltage transfer ratio, V sub O over V sub I, is R2 over R1 plus R2. At lower frequencies, This capacitor still looks like an open circuit, but this one now begins to look like something other than a short. And so at low frequencies, the voltage transfer ratio begins to drop because this capacitor introduces an impedance in series with R1. And finally, if you go to very high frequencies, this capacitor now begins to draw substantial current. Its impedance is no longer negligible, and the output begins to drop because the current drawn by C2 causes a drop in R1 and C1. So the Bode plot of such a circuit with appropriate choice of the constants is one which has, if I plot magnitude of V sub O over V sub I on a log scale versus log omega, has a Bode plot which looks more or less like this. Falls off with a slope of 1 at low frequencies, falls off with a slope of -1 at high frequencies, and has some middle region in which it is relatively flat. Now, we need to look specifically at the transfer ratio, V sub O over V sub I, complex amplitudes. And we'll speak of this as the voltage transfer ratio, A of S. It's a complex number, and it is dimensionless. It's a voltage divided by a voltage. And I can write immediately, just thinking of this circuit as a voltage divider. This is the lower arm of the divider. This series combination is the upper arm of the divider. We can write an expression for this in voltage divider terms. The impedance of the lower arm is R2 in parallel with 1 over C2S. So that appears in the denominator, R2 in parallel with 1 over C2S. And then the impedance of the upper arm is R1 plus 1 over C1S. So in the denominator, I have to have R1 plus 1 over C1S. And what I mean by in parallel with, just to be perfectly clear about it, R2 in parallel with 1 over C2S is R2 times 1 over C2S, just as with a voltage divider, divided by R1, and a resistive voltage divider divided by R1 plus 1 over C2S. So if I substitute this relationship back here and here, you get a bit of an algebraic mess, but with a little patience, you can end up, I'm not going to go through the details, but you end up with an expression for A of S, which looks like this. There's some constant K. In the numerator, S. In the denominator, S squared plus S squared plus beta S plus gamma. And these constants, K and beta and gamma, are collections of the coefficients, R1, R2, C1, C2, and they are all positive numbers. Positive, of course, real numbers. We've introduced, since S is still, since we haven't set S equal to J omega, there are no imaginary numbers around. All the expressions and all the variable S, A, K, beta, and gamma are real numbers. So this is the result. K and beta and gamma are collections of the constants. And if you work it through in detail, you can evaluate all those, but for our purposes here today, it's not really important. What I want to do is look at this transfer ratio, dimensionless transfer ratio, and see what we can learn about the properties of the circuit. Let me repeat it here. A of S, which we defined as V0 complex amplitude divided by V sub I complex amplitude, is a constant K times S over S squared plus beta S plus gamma. And all these constants, beta, gamma, k, are positive real numbers. Let me write this out now. Just multiply both sides. Multiply by v sub I and multiply by this quadratic. So we get v sub O complex amplitude times s squared plus beta s plus gamma equals k times s. K times s times v sub I. Same equation, just cross-multiplied. Now, what can we say about the behavior of this voltage transfer ratio by looking at this expression? First question we might ask is there a frequency that is some value of s such that v sub O bar equals 0 for finite, that is non-zero v sub I. This needed a bar. Is there some value of s such that I can have an input represented by its complex amplitude v sub I, but the circuit produces no output? Well, pretty clear that there is, and it is s equals 0. That is, this frequency is s equals 0, which means, of course, nothing is changing with time, or we have a DC condition. At that frequency, may seem trivial, but a real frequency, s equals 0, at that frequency, there is no output from this circuit because both these capacitors, which have impedances which vary like 1 over Cs, the impedances of these capacitors, as I go lower and lower in frequency toward 0, these look more and more like open circuits. And if this capacitor is an open circuit, there is no way for a signal here to get through to here. This is an open. So that checks what ought to be the case intuitively. Such frequencies in a transfer ratio, such frequencies are called zeros. This is called a zero. Not because it is 0, that's also true. But any frequency which is such that you don't get an output when you put in an input is called a 0. Now, the second question is there a frequency, some value of s, such that v sub O, the output, is finite, non-zero, for v sub I equal to 0. So the second question is, if we do not excite the circuit with that input voltage, if v sub I, complex amplitude, is equal to 0, so there's no excitation, is there some frequency at which the output can be non-zero, in which there can be a non-zero output voltage? Well, if you look back at the equation, the transfer function expanded out, clear to fractions, it's pretty clear that there is such a frequency. It is the frequency for which this quadratic vanishes. In other words, if s squared plus beta s plus gamma equals 0, if this is true, if this condition is satisfied, if that quadratic equals 0, then I can have a non-zero output. V0 bar can be non-zero. And even in the presence of some v sub I, which is 0, the equation is satisfied. That is, if I let v sub I equal 0, the right side has got it, the left side of this equation must equal 0 somehow, and the only way it can equal 0 for some non-zero output voltage is if the quadratic vanishes. Such frequencies, and because this is a quadratic, there are two such frequencies, two such roots. I'll call them S sub A and S sub B, are roots, are the roots of the quadratic. And so for S equal to S sub A, or S equal to S sub B, the quadratic vanishes. And we can have a finite V0 in spite of no input. Such frequencies are called, in the nomenclature of the trade, poles. So this transfer function has one zero that happens to be at the origin. It has two poles which are at S equals minus S sub A and S equals minus S sub B. If by S sub A and S sub B, I mean positive numbers. When S equals minus S sub A, the function vanishes. When S equals minus S sub B, the quadratic vanishes. This can be represented on a complex plane by simply locating the poles and zeros. That is, if this is the real axis and this is the imaginary axis, the origin is here, the 0 was at the origin, now represented by a circle there. And the poles, because S sub A and S sub B are functions of the parameters, they are positive real constants, the frequencies at which this thing vanishes are on the negative half plane, perhaps like this. That is, this could be minus S sub A, and this minus S sub B. What I have done in, just let me be a little bit clearer about this, is what we are saying is that S squared plus beta S plus gamma can be written as the product of two factors. The factors are S plus S sub A and S plus S sub B. Now, it may not be self-evident that this quadratic can be factored into two first-order terms. You may ask, well, this is a quadratic, why can't it have imaginary roots? It will turn out, if you work through the algebra and crank out what this transfer function is, it will turn out that for all possible values of these parameters, I'm going to end up with two real roots of the equation. It is not possible in this circuit, in spite of the fact that it has two energy storages, it is not possible to get a quadratic with imaginary roots. You just have to take that on faith at the moment. But by representing it in this manner, I mean that the two roots are S equals minus S sub A. That is, when S equals minus S sub A, this term vanishes, and that's one root. And S equals minus S sub B is the other root. And those are as I plotted them here. This is factorable. The two linear factors, S plus SA, S plus SB, SA and SB are positive numbers depending on the coefficients. And so the roots of this, I didn't say it quite correctly over here, I said SA and SB are the roots. The roots are actually minus SA and minus SB, which is clear once I write it in that form. That is, when S equals minus SA, the function vanishes, and when it equals minus SB, the function vanishes. So I have a pole zero diagram, this is the complex plane, which looks like this. And you recognize that except for the factor k, except for k, which appeared in this quadratic as a multiplier out front, except for the factor k, this pole zero diagram describes completely the transfer function. That is, from the pole zero diagram, I could write, if I didn't know the circuit, if I didn't know what circuit we were starting with, if all I had was this pole zero diagram, I could write that A of S is some constant, some scale factor, times S over S plus SA times S plus SB. Knowing the locations of the poles, the two poles in the denominator, and the zero, the single zero in the numerator. And all I would be missing from the point of view of the actual circuit is the constant, the scale factor that goes out front. So the complex plane representation of poles and zeros associated with the transfer function, with this transfer function, contain all the information about the dynamics of the circuit. Say that again. If you have a pole zero diagram for a circuit or any linear system, that diagram locating the poles and zeros contains all the information about the dynamic behavior of that circuit or system, except for some scale factor. Not that it's unimportant, but all the dynamics is contained in the portion of the expression that depends on S, the complex frequency. So, to review, we've found roots of the numerator, which we call zeros, roots of the denominator, which we call poles, plot them on a complex plane. Think about what the poles must represent. The poles are frequencies at which the denominator reduces to zero. They are frequencies at which the circuit can have an output without an input. So if I want to represent the circuit as having an output without an input, let me redraw it and simply replace the input voltage by a short circuit. So here's the circuit redrawn. I won't label all the coefficients. The voltage V sub I, which we defined here, we're now setting to zero. That is, we're letting V sub I be identically zero. And we know that at certain frequencies represented by the poles, we can still have a V sub O, which is not equal to zero. How can that be interpreted? If a network is not being driven by a source of some kind, it must then exhibit its natural behavior, its characteristic behavior, its unforced behavior, or in terms of the way a physicist would speak of it, it must exhibit its eigenfunctions, which occur at particular eigenvalues, characteristic frequencies. Therefore, the behavior of this circuit with the input shorted and a particular frequency represented must be the unforced or undriven natural transient response of the circuit. There's no source. We have found two frequencies, minus S sub A and minus S sub B, at which it's possible to have an output voltage even though there is no input. And the only possible interpretation of that is that those frequencies must represent the natural frequencies of the network, and the responses, we see just one here, V sub O, but I could label any other voltage or any current in the network, and it would have the same frequency dependence. The responses are the unforced natural behavior of the circuit. So in circuit terms, we can say that the time function here, that is, remember that a complex amplitude represents a time function. The corresponding time function, V sub O of t, must be complex amplitude V0 e to the st, where s equals, let's say, minus s sub a. This time function is not a real number. It's got a complex amplitude, but we can always get back to the real world by taking the real part of it. This means that the time function that we can see anywhere we look in this network, we're looking just here, must be of the form V0 of t equals, if I take the real part of this, e to the st, where s is a negative constant, is a real number, so it's only the real part of this complex amplitude, which I'll represent as a. V0 of t is a, e to the minus s sub a t, plus some other constant b times e to the minus s sub b t. And this is the transient response of the network. That is, left to itself, unforced, dump some energy in the capacitors and see what happens. You get responses, a response, which is the sum of two exponentials with different time constants. The time constant here, 1 over s sub a, time constant here, 1 over s sub b. Different natural frequencies, two different exponentials, and the general form of this voltage, V sub O, the natural unforced response, is the sum of those two decaying exponentials. So what we've seen at this point is that by focusing on the poles, the frequencies at which the denominator vanishes, we have in fact focused on the natural frequencies, the unforced natural frequencies of the network, the ones at which it will behave, the frequencies at which it will behave under unforced conditions, no source. And this comes from the transfer function of the network. There is another utility, and let me take the transfer function in this form, expanded, rewrite it here, so it's V sub O times s squared plus beta s plus gamma equals k s V sub I bar. This is a bar. Now remember that V sub O and V sub I in the analysis were the complex amplitudes of the excitation and the response. That is, the excitation was of the form V sub I of t equals complex amplitude V sub I e to the st. And V sub O of t, because this is a linear constant coefficient, the circuit is linear with constant coefficients, the excitation, e to the st, appears as a factor in the variables everywhere. The output is V sub O bar e to the st. The only difference between the input and output are the complex amplitudes are different. The time dependence is always e to the st. Now, up to this point, in an analysis like this, we would say, okay, let's let S equal j omega. Let's let S equal j omega. Take the real part of the complex amplitude, e to the j omega t, That requires putting the complex amplitude in polar form and combining the angle with omega t. Take the real part and you get a number times cosine omega t at some angle. You're back to a time function, a cosine sine function, which is implicit in s equals j omega. Here we've not let s equal j omega. I'm just going to carry it as s. And recognizing that the result of plugging v sub o and v sub I in this form into a differential equation must yield that expression enables me to write the differential equation directly. The differential equation from which this transfer function results is d squared v sub o dt squared plus beta dv sub o dt plus gamma v sub o equals k d v sub I by dt. And that must be then the differential equation of the original network, of this network. Now you may say, what's the point? I can get the differential equation directly. Well, certainly you can. You can write, if you assign this as a reference node, this is plus v sub I and plus v sub o here. V sub o is one node to reference voltage. If I assign another node to reference voltage here, call that v sub m, then I can write two node equations, two simultaneous node equations. In this one, for example, thinking now in terms of the time functions of which these are complex amplitudes, I would have little v sub little o, the time function, divided by r is the current out through here, and C2 times dv sub o dt is the current through here. Add up the current through here, set it equal to 0, so on. Solve the two simultaneous equations. Eliminate v sub m to get a differential equation, which will be this. The advantage of doing it this way is that instead of solving simultaneously two differential equations in the variables v sub o and v sub m, and then eliminating v sub m, instead of doing that solution in the time domain, if you will, we do the algebra here in the frequency domain, and then recognize that the differential equation must be this, because if I substitute in these variables and divide out the e to the st, that's what I'm left with. So the transfer function has the additional virtue of enabling you to take a circuit of arbitrary complexity and go back and write the differential equation, which must relate two variables, a driving variable and an output variable in that circuit. And as with sinusoidal steady-state solutions, this analysis, the analysis with complex amplitudes and a complex frequency S, is somewhat easier. It's always easier to work with algebra than it is to work with the differential equations. Before I go on and look at a second example, very briefly, let me just emphasize what we've done here. We said that if the frequency of voltages or currents in this network was such that the characteristic equation back here was such that this equation is equal to 0. That is s squared plus beta s plus gamma equals 0. That is the characteristic equation for this network. That is, if we started with this differential equation and substituted in a e to the st, I get s squared plus beta s plus gamma a e to the st equals the other side, and that would be the characteristic equation. We've said that the roots of the characteristic equation, which frequencies we call poles, are such that if the responses in the circuit are at that frequency, S sub A or S sub B, or more generally, exponentials, both of them simultaneously, then the network can have an output. There can be currents and voltages anywhere in this network without an excitation. And that condition, by definition, is what we mean by the unforced natural response of the circuit. If I dump some energy in the capacitors, stand back and let the circuit behave, what we get is the undamped natural response, time response, transient response. And it occurs, in this case, with two exponentials of different frequencies, S sub A and S sub T, the sum of two exponentials giving us the voltage at this point, and the same would hold true for any voltage or any current. In making this interpretation, we have departed from the previous convention in which we insisted at the end that S equal J omega, and we said, we'll let S equal something else. We'll let it equal a pole frequency. And in that case, we can write time expressions, which are the real part of that complex time expression, and get the actual time function that represents the behavior of the circuit. Let me look quickly at one other example and draw the pole zero diagram. This is a band stop, a narrow band filter, one which we talked about previously. This is RLC. If we put an input here, V sub I, complex amplitude, and ask what is the output here, V sub O. Again, voltage divider thinking. These two elements in series comprise the lower arm of the voltage divider. This element is the upper arm. So V sub O over V sub I. The voltage transfer ratio is just the impedance of the lower arm, which is LS plus 1 over CS, divided by that impedance, LS plus 1 over CS, plus the impedance of the upper arm, which is R. And if I clear numerator denominator of fractions, we get LC S squared plus 1. And downstairs, LC S squared plus RCS plus 1. And if I do just one little bit more of manipulation on that transfer function, which is the divide through by LC, it is simply S squared plus omega naught squared over S squared plus 2 alpha S plus omega naught squared, where omega naught squared equals 1 over LC. It is the undamped resonant frequency of this series LC combination, and 2 alpha is equal to R over L, which is the damping factor. Alpha is the damping factor. We can factor numerator and denominator. The zeros of this transfer function are just plus J omega naught and minus J omega naught. That is, if I let S equal J omega naught, S squared equals minus omega naught squared, it's 0. If I let it be minus J omega naught, S squared is minus omega naught, and that cancels as well. That reduces the numerator to 0 as well. So there are two zeros, and they are minus J omega naught plus J omega naught. There are two poles. And if I assume that alpha is less than omega naught, so that we are dealing with an undamped, with an underdamped circuit, the only kind we've dealt with in any detail in this subject. If we're dealing with an underdamped circuit, then the poles occur at frequencies S sub A, S sub B equal minus alpha plus or minus J square root of omega naught squared minus alpha squared. And that's just applying the quadratic equation to this denominator, setting it equal to 0 and finding out what the roots are. Or I could write it as minus alpha plus or minus j omega d, where omega d is the damped natural frequency. Omega d squared equals omega naught squared minus alpha squared. The smaller alpha is, the closer omega d is to omega naught. Okay, let's make a pole zero diagram. Real axis, imaginary axis. This is the S-plane. There are two zeros at j omega naught and at minus j omega naught. And there are two poles which, depending on the value of alpha, fit on this semicircle. This is minus alpha here. And let me say that they're right here. I'm sorry, this is minus alpha for alpha equals omega naught. That defines this semicircle. So I really ought to be clear about this and saying, calling it minus alpha, I ought to call it minus omega naught. And the intersection with the vertical axis is at j omega d and at minus j omega d. So we got a pole zero pair in the positive half plane, a pole zero pair in the negative half imaginary plane. And the zeros are off the axis to the left. The value of the intercept here is just alpha. You can reason out why the zero should be there at least, because at the resonant frequency, when omega equals omega naught, the impedances of these two reactive elements, the capacitor and the inductor, are equal and opposite. And so the impedance from here to here is 0, precisely 0 at omega naught, and there's clearly going to be no output voltage at that frequency, thus a 0 at either plus j omega naught or minus j omega naught. The behavior associated with the poles is a little more complex. I'm not going to go through it in detail, but the entire dynamics of the circuit, except for the scale factor, which in this case I guess is 1. Yeah, there is no scale factor. The entire dynamics of the circuit, potentially, except for the scale factor, not dynamic in nature, is contained in that pole zero diagram. There is one more interpretation you can give to the complex plane, the S-plane, and the pole zero diagram. And that is to imagine that you lay on top of the complex, on the top of the S-plane, I call it the complex plane, I'm really calling it the S-plane, where I'm plotting the roots of the numerator and denominator. Imagine laying across this sheet, across this plane, a very large sheet. You lay on the plane a very large sheet of rubber, elastic material, which is isotropic, which has the same elastic properties in all directions, and which has the capacity being stretched very far without breaking. And all the way around the perimeter of the plane, way out at infinity in all directions, you nail that piece of rubber down to the table. And wherever there's a 0 in the complex plane, you drive a nail in and nail it down to the table at that point. And wherever there's a pole, you lift it up and you stick an infinitely long bar under that pole, so that at that point, at exactly that point, the rubber sheet is way up here, up at infinity. And then if you visualize yourself walking along the imaginary axis, if you can imagine a cut through that diagram, nail down all around the edge, nail down here, very, very high here and here, if you can imagine a cut walking along that diagram as your frequency moves from 0 up to j omega, up to omega somewhere, from omega equals 0 to non-zero omega. The nature of the slice of that complex shape is exactly the magnitude of the transfer function for S equals j omega. It's true on any of these S-plane diagrams. Here, the sheet, of course, nailed down all around the edge, nailed down at these two zeros, and pushed up infinitely high at these two poles. If you imagine walking up this imaginary axis and looking at a cross-section of this stretched sheet, you can get a sense of what the magnitude of how the magnitude of the transfer function behaves. These two poles push it up in this area, so for very low frequencies there is transmission through the network. And that corresponds to the fact that at low frequencies the inductor looks like an open circuit and V sub O is just equal to V sub I. As I get toward the zeros, the transmission drops and goes to zero at these, exactly to zero at these frequencies. And as I go beyond that frequency to higher frequencies, again we're out to a region where this pole has got it pushed up. And for high frequencies, the transmission will be good because the inductor looks like an open circuit as I go to higher and higher frequencies, so VO equals V sub I. In the vicinity of the zero, the fact that it's pushed up very high near the zero means that this decline from a value of 1 in close to 0 and then back up to a value of 1 occurs very sharply. And the closer the pole is to the 0, the sharper that transition either side of the 0 will be. So by looking at the S-plane diagram for the circuit, you can get a sense of how the magnitude of the transfer function must behave without writing it out and doing the complex arithmetic and plotting magnitude and angle. So let me summarize. What I've said is that if you use an impedance approach to the analysis of a linear circuit representing R by R, L by Ls, its impedance, capacitance by 1 over Cs, its impedance. Use straightforward algebra then to form an impedance. I've talked here about transfer functions, but it works equally well for impedances. To form an impedance or an admittance or the transfer function, and express that transfer function as a ratio of polynomials. The function of S, the polynomial ratio, apart from any constant out front, the function of S represents completely the dynamic behavior, or contains completely the dynamic behavior of that circuit. If we want to know what the frequency response is, that is the sinusoidal steady state response, we take the transfer function of S, insert S equal j omega, a little complex arithmetic to get it in the form of magnitude and phase in polar form, multiply that polar form by e to the j omega t, take the real part, and we've got the time function, the sinusoidal time function at the output. We plot the magnitude and the angle on a Bode plot, and we have a graphical representation of the frequency response. If we want the unforced, the undriven, the natural transient response, time domain behavior, if we want the natural time domain behavior of the circuit with no forcing, no drive, we set the characteristic equation, the denominator of the transfer function equal to 0, and its roots are the natural frequencies. If we've done that here, you see the form of these roots. They are in the form of a minus alpha plus j omega d. The form of that is a damped cosine, or a damped sine, doesn't matter. So in this case, the natural frequencies are damped sines and cosines, and we can infer that from the S-plane diagram alone. If we wish to, for some reason, get back to the differential equation, which is, I suppose, the most fundamental way of describing the behavior of these circuits or systems, if you want to get back to the differential equation, You do it by looking at the transfer function multiplied out in this form, recognizing that the time functions are defined in terms of the complex amplitudes, and the natural frequencies, represented here by S, are defined in this manner, which means that this differential equation must produce that relationship among complex amplitudes. So having only this relationship, I can go backward term by term to build up the differential equation. The transfer function expressed as a function of S, or any other relationship expressed that way, impedance or admittance, contains all the information you need about the dynamics of the circuit, either in the frequency domain or in the time domain. And thinking about it in those terms allows you to see rather straightforwardly the relationships between time domain behavior, natural transient response, homogeneous solution behavior, and frequency domain behavior. Thank you for your attention.